Today we're going to be taking notes on superposition and polarization. In order to discuss superposition, we need to first talk about interference. Interference is when two waves meet within the same medium. The principle of superposition is when two or more waves meet, the resultant displacement is the sum of the individual displacements. There are two different kinds of interference. With constructive interference, we have two waves that are interfering with each other, and they create a displacement in the same direction. For example, we have one wave here that is in red, that is of 1 unit in height for its amplitude, and we also have another wave that is in blue of the same magnitude in its amplitude. When it does meet and cross, its resultant amplitude is the sum of both of the amplitudes. Down here, before the interference, we see that the amplitude has a negative value, and so this is the trough, and we have two waves that are running into each other, and as they do during the interference, again, the displacement is the sum of both of the waves. With destructive interference, the two waves that are interfering have a displacement in the opposite direction. So if we have a positive value for its amplitude in one wave, and there is a second wave that is moving towards the first wave that has a negative amplitude, when they meet during the interference, you would have a resultant that would be 0. Therefore, it would pretty much just annihilate the amplitude, and it would have an amplitude of 0. The waves do continue, and when they do continue in the direction that they were going, they will return back to its original amplitude. Down below here we have two amplitudes of varying sizes. So here we have an amplitude that has a value of 1 unit that is moving to the right, and we have a value of 2 units that is a negative amplitude that is moving to the left. And when they meet up, you actually have to add the amplitudes together. So here we have a -2, and here we have a +1. So the amplitude that is resultant from the two waves that are meeting would be in the negative direction, as seen in this green line right here. So constructive and destructive interference is when two waves of the same frequency superimpose. They are overlapping upon each other. And this is how we get constructive interference, or we can get destructive interference. So if you take a look at this picture here, this is 1 full wavelength plus 1 full wavelength. If you get two of these that are meeting, you would get twice the amplitude in the crest part of the wave as well as that of the trough. Here, if you have opposing amplitudes, here it is positive, here is negative, so they are opposite, then they would negate each other and the amplitude that results would be a 0. Let's take a look again at the principle of superposition with this example. Now remember that when two or more waves meet, the resultant displacement is the sum of the individual displacements. So we should be able to figure out, calculate, and graph the resultant wave that would happen when these two waves meet. Here we have wave 1, which is with red dots, and then we have a second wave that has blue dots. Given that we know that each square is 1 unit, we should be able to find the resultant displacement. So let's take a look. We have the grid down here for points A all the way to U, and we're just going to do a select few so you can kind of get an idea of how to find the resultant displacement. If you're looking at point A here, we have the displacement for the first wave, which we will call the one in the red. We have a displacement of 0. For the displacement for wave 2, which is with the blue dots, it is also 0. Therefore, if we find the sum of this is obviously 0. Point C shows that the red wave has a displacement for 2 units, which is located here. And for the displacement for the second wave, we are twice that, so we have 4 units for the amplitude. The resultant, because this is above the x-axis, we know that we have to add them. So we get a total of 6 units. For point G, we have a displacement for wave 1 as being -2 and for wave 2 being -4. Therefore, because they are both in the negative direction, we add them and we get a -6. When you plot all of these points after finding all of the sums of each parts of the points down here from A through U, you should be able to get a new graph. And this shows the resultant displacement when both waves 1 and 2 superimpose. We know that light consists of electric and magnetic waves. The two fields are perpendicular to each other, which is seen here. We have the electric field, which is vertically polar, and here we have a plane that is vertical to that of the electric field, which is the magnetic field. You can see that the direction of the wave of propagation is shown going from right to left at this angle. Because we are going to be discussing polarization of light, we are going to be focusing on the electric fields only. Take a light source, such as a light bulb, which contains a large number of molecules that emit light. If the particles are experiencing the same position of their electric fields, then the light is said to be polarized. So if all of the particles, all of the molecules are moving in the same plane, then it would look like this. This polarization can be vertical, as in this example, but it can be in any other plane. As long as the wave is oscillating on any one plane and the particles are following that plane, then the light is termed as being polarized. In reality, light is composed of many light waves with electric fields in practically every direction. So just imagine that, yes, you do have some molecules that are oscillating in a vertical direction, but then you also have light that's oscillating with the electric fields in a perpendicular direction. There's also light, the molecules that are oscillating at an angle in their own plane. So when we have electric fields that are oscillating in a multitude of planes along the direction of propagation, then we call this kind of light unpolarized. That would look more like this. Here we have only two planes showing. We have a vertical and a horizontal oscillating electric field. But there could be many more that are in degrees that are slightly off from the vertical and the horizontal. There are ways to represent electric fields that are unpolarized, propagating in the same direction. Here is one example. The figure here on the left is a 3D representation of unpolarized light, and it is the most involved. Each of these is a plane the electric fields are oscillating. So, for example, here we have a vertically oscillating electric field. That would be maybe this one right here. But there would be another one, and another one, and another one, and so this one is very complicated. There is a second figure right here that shows a more simplistic representation of unpolarized light. And each arrow here represents the planes for each of the electric fields. And if we were to try and represent the direction of propagation, it would be like in this direction here, and there would also be another line over here in the 3D representation with the energy propagating in this direction. So all of these would be sharing the same direction. We can simplify unpolarized light even further by the third figure right here. It is simplified down to the horizontal and the vertical planes only because all of the planes of the electric field that are oscillating can only be vertical or horizontal components. So we know that there are more planes, such as in the second diagram. However, this is just a more simple version to let you know that there are vertical and horizontal components. And if you were to orient this last diagram, you can pretty much get any angle that is shown in any of these other diagrams. So the question is, how do we get polarized light if light is unpolarized in most cases? Here is an example of unpolarized light, and we're trying to make it into where we have polarized light, which means that we're only trying to get one plane of the oscillations of the electric field. We use a process called polarization. This is where we transform unpolarized light into polarized light. How do we do this? Well, there are a few ways that we can polarize light. We can use a Polaroid filter. We can reflect the light off of a surface. Polarization can also happen from refraction, such as when we use crystals like quartz. And that would mean passing the light through a crystal, and then by passing through it, we would create polarized light. And then another one is by scattering from gases. Let's take a look at the example of a Polaroid filter. So here we have multiple planes of the electric fields of unpolarized light. When the unpolarized light is transmitted through this filter, the light on the other side will have half the intensity and with oscillations only in one single plane. It will become what we call polarized. How is this possible? Well, a Polaroid is made from long chain molecules that are positioned with their axis perpendicular. So here's the example where the molecules are positioned perpendicular. So we call this the polarizing axis. So these long chain molecules are positioned as vertical, and the molecules absorb light that is polarized along their length. Whatever hits the molecules, then they would be absorbed, while allowing the plane that is not touching the molecules to go through. Look at the example with the flashlight shining onto the two Polaroid screens. Notice that the two filters here are both vertical filters and only allow vertically oscillating waves to pass through. If sunlight were to enter the first filter, only the vertical components would pass through. The second filter ensures that any horizontally oscillating waves of light that are present will be blocked, so that only the vertical components are present at the very end. This technology is used for polarized lenses of our sunglasses to help eliminate the glare from the sun. A great analogy is the picket fence example. A picket fence can act as a polarizer by allowing vibrations represented by the rope that are parallel to the gaps to pass through while blocking any oscillations that are perpendicular to those gaps. If two picket fences are positioned so that the pickets are aligned vertically, then the waves will be able to pass through both fences. If, however, the second fence turns sideways, so the gaps are horizontal, then the vertical oscillations that go through the first picket fence will pass through. However, they will be blocked when they try to go through the second fence. Looking at the flashlight example up here, you will see that by having a vertical polarizer followed by a horizontal polarizer, there would be no light that can pass through, and it would be dark on the end. Let's look at Polaroid filters in action. Here we have a lady who has two filters in front of her face. In photo A, located over here on the left, both polarizers are vertical. We are able to see her smiling because the light that was incident on the first filter became polarized, and the second filter was in the same orientation as that of the first filter, which then allowed that polarized light to pass through, and we are able to see the person behind the two filters. In photo B, on the right, we have one vertical and one horizontal Polaroid filter. The filter on the front is vertical, and the filter on the back is positioned horizontally. The unpolarized light that is incident on the first filter would pass through. However, because the light that passed through the first filter is vertically polarized, it is unable to pass through the second filter, which is horizontally oriented. And this is why we see nothing here. It's very dark. Let's talk just a little bit about the other ways that light can become polarized. Unpolarized light can also become polarized by being reflected on surfaces. What happens here when, let's say, the sunlight is traveling towards the water, and after reflecting off of the surface of the water, the light reflects as polarized light. Because we know the light coming off the water is horizontal, we can have sunglasses with vertical polarizers that block out the reflected light from the water. This helps to cut down from the glare that we see reflecting off of the water's surface. We can also see polarization occur during refraction, and this is when we use crystals such as quartz. Here, for example, we have the light is incident to the surface, and as the light goes through the medium, the ray diffracts, and through this diffraction becomes polarized. We can also polarize by scattering, and this is scattering from gases. This is a much more complicated process, so in a nutshell, when unpolarized light is incident with molecules of gases, the molecules absorb the incident light and re-radiates it in different directions, resulting in partial polarization. There's some terminology that you need to know. When we say polarizer, it is an optical filter that allows only one specific polarization. The analyzer is a polarizer, except its position is always the second filter in a system that is polarizing light. Here we have a diagram of a light source of unpolarized light that is entering into a polarizer and then going to the second polarizer. So an analyzer is pretty much just a polarizing device that indicates the direction of the wave's vibration. It has the same purpose as that of a polarizer. It's just given a different name because it is the second filter in the process of polarizing light. An incident ray is a ray of light that strikes a surface. So this would be, for example, the unpolarized light that is coming towards the surface before the interaction and then becoming, for example, the polarized light by reflection. Here we have the incident ray hitting the mirror's surface, and we also know that the angle of incidence is the angle that's between the incident ray and the normal, which is the perpendicular line to that of the surface. The reflected ray is the light that is reflected by the surface, and then the angle of reflection is the angle between the normal to the surface and the reflected ray. Malice's law is another concept about polarization. And what this states is that when plane polarized light is incident on the analyzer, remember the analyzer is the second Polaroid filter in the system, the intensity I of the light transmitted by the analyzer is directly proportional to the square of the cosine of angle between the transmission axes of the analyzer and the polarizer. This is denoted in the equation I equals I naught cosine squared theta. So let's say we have some polarized light that has an intensity of I. And this light is traveling towards the first Polaroid filter that is vertically arranged. So the direction of the ray that made it through the first filter is vertical. It now reaches the second filter in the system that is arranged at some angle to that of the plane of the oscillation of the wave. We can work out how much of this ray gets through the analyzer by doing a vector projection. This is similar to if we had to resolve some force in some direction that is at an angle. To work out how much of the polarized light makes it through the analyzer, we need to look at how much of the plane of polarized light is in orientation with that of the analyzer. So this is our ray, which is the amplitude of the wave, and we will give that the variable A naught. Over here, this is the line of the analyzer, and that is located here. The angle between these two is theta. The amount of this ray's amplitude, A, that gets through will be this part right here, and we can resolve that as being A naught cosine theta. A naught is the initial amplitude that we have at this point, so it would be A naught cosine theta. Now, to get to Malice's law, which refers to the intensity, we know that A equals A naught cosine theta. We also know that intensity is proportional to the square of the amplitude. So what I'm going to do is I'm going to put I into this equation to get this equation down here. But first what I want to do is I just want to square A, so then that way I can make sure that I just have to plug in I. So when you do that, all you have to do is square everything, and that's how you get a squared equaling a squared naught cosine squared theta. And then you just plug in I for both of the amplitudes, and you get the equation that is in our data booklet as I equaling I naught cosine squared theta. Using this equation, what we can see is with this angle of cosine theta, if the angle of theta were to be 0, the cosine of 0 would give us 1. And if the direction of the plane polarized light is in line with that analyzer, then all of the light passes through the filter. If theta were 90 degrees, then the cosine of 90 would be 0. So if the filter is 90 degrees in orientation to that of the polarized light, then none of the light will pass through. Here's an example. Go ahead and try and solve this problem and then check your answer. Light from an unpolarized source is passed through a plane polarizing filter. A second filter is placed at 30 degrees off axis from the first filter. Determine the proportion of the original light intensity that passes through the second filter. Here is a picture of the situation that you're trying to solve. Over here on the left, we have the unpolarized light, and we will go ahead and term that as I. It will pass through. It will pass through the polarizer, which is the first filter, and you would get an intensity of I naught. This polarized light will then pass through a second filter, the analyzer, and we'll just say that that's I sub F for the final intensity. We want to try to find the proportion of the original light intensity that passes through the second filter. Here is the vectors. So this is I naught, and then this is the angle of the analyzer. This is theta, and when we solve for this vector here of how much of the polarized light passes through the analyzer, we have A naught cosine theta. When you plug everything into the I equals I naught cosine squared theta, we plug all of this in and we have 30 degrees for the angle for theta. And now we know that we have 0.75% of I naught right here. Okay, so our notes are finished. Be ready to use this information in class, and thanks for watching.